Hello students, this is Dr. A classes for BTech students. Today's lesson covers discussion on Earth's internal and external structure. It is designed to provide BTech civil engineering students with essential geological knowledge. Learning objectives of the courses: identifying and describing the major layers of Earth, explaining the physical and chemical properties of each layer, describing the methods used to study the Earth's interior and exterior, understanding the concept of isostasy, identifying major plates and explaining how they move, explaining the driving forces of plate tectonics. Overview of Earth's geology. Earth's structure and processes are broadly divided into two main aspects: interior geology and exterior geology. Interior focuses on layers beneath the surface, crust, mantle, and core. It explores into the composition and dynamics of Earth's interior. Exterior geology focuses on the features and processes observable on Earth's surface. The detailed discussion on surface processes will be covered in our next topic, physical geology. It will include weathering, erosion, sedimentation, volcanism, and earthquake. Exploring Earth's interior. Exploring the Earth's interior is a fascinating topic in geology as it unveils the mysteries of what lies beneath the surface. Earth's interior is composed of several concentric layers, each with distinct characteristics. The direct exploration of Earth's interior is not possible due to the immense depth, extreme temperature, and immense pressure within the Earth. These conditions make it impossible for humans or current technologies to directly access and study the deeper layers. For example, the Kola Superdeep borehole in Russia at 12,262 meters represent a minuscule fraction of Earth's radius, which is 6,371 kilometers. Since we cannot access the deep Earth, scientists use indirect methods to study it. Scientists continue to refine their understanding of Earth's interior through ongoing research and advancements in technology. New techniques and instruments are constantly being developed to improve our knowledge of Earth's deep structure and processes. Earth's density and its internal structure. The mean mass density of the Earth, calculated from its size and motion around the Sun, is 5.527 gram per cubic centimeter, which is greater than the density of most rocks found at the surface of the Earth. The density of the rocks at surface rarely exceeds 3 gram per cubic centimeter. The density of sedimentary rocks averages 2.3 gram per cubic centimeter, and the density of igneous rocks averages 2.7 gram per cubic centimeter. Therefore, for the mean density to be around 5.5 gram per cubic centimeter, there must be denser material inside the Earth at deeper levels. The study of the elastic waves generated by earthquake confirms this inference. The study suggests that our planet has metallic core consisting of two metals, iron and nickel, with the density ranging between 9.9 to 13.1 gram per cubic centimeter. The outer core, the outer core is believed to be a fluid having density between 9.9 to 12.2 gram per cubic centimeter, whereas inner core is solid with a density of 12.8 to 13.1 gram per cubic centimeter. Above this heavy core is the zone called mantle, which consists of silicates of iron and magnesium oxide. This zone and magnesium oxide having density intermediate between the crust and the core, which is about 4.5 gram per cubic centimeter. The crust overlies the zone, i.e. the mantle. Indirect methods. Scientists rely on indirect methods to understand Earth's structure and composition. These methods include seismology. This is arguably the most crucial method. Earthquake generates seismic waves that travel through Earth's layer. By analyzing how these waves are reflected, and absorbed at different depths, scientists can identify distinct layers or determine layer properties. Geothermal gradient. The temperature increases with depth within Earth. By measuring this temperature gradient, scientists can estimate heat flow, infer mental dynamics. Gravity. Earth's gravity is not uniform. Variation in the gravity readings can indicate density differences, large-scale structures. Volcanism. Volcanic eruptions bring material from deep within the earth to the surface. By analyzing the composition of volcanic rock, scientists can infer mental composition, understand mental processes. Meteorites. Meteorites are the remnant of the early solar system. By studying the composition of meteorites, scientists can infer the composition of the early Earth and gain sight into planetary formations. Ongoing research and advancements. Exploration of Earth's interior is an ongoing endeavor. By combining observations from various sources and employing advanced techniques, scientists are steadily piecing together a more comprehensive picture of our planet's deep structure and dynamics. Geophysics. Continued development of seismic tomography and other geophysical techniques allows for increasingly detailed images of Earth's interior. High pressure experiments. Laboratory experiments are conducted to simulate the extreme pressure and temperature found deep within the Earth. These experiments help researchers understand how materials behave under such conditions. Computational modeling. Sophisticated computer models are used to simulate Earth's internal processes such as plate tectonics and mantle convections. These models help integrate data from different sources and generate new hypotheses. Space-based observations. Satellite can provide valuable data on Earth's gravity field, magnetic field, and topography, which can be used to refine our understanding of Earth's interior. Earth's layers: crust, mantle, and the core. These observation indicates that the Earth is composed of several distinct layers. Crust, the outermost layer of Earth, it is relatively thin and divided into two types: oceanic crust and continental crust. Mantle, the thickest layer located beneath the crust, it is primarily solid but behaves like a viscous fluid due to high temperature and pressure. Core, the innermost layer of Earth, it is composed mainly of iron and nickel. The core is further divided into two parts: outer core, liquid layer, responsible for generating Earth's magnetic field; inner core, solid due to immense pressure. Earth's crust. The Earth's outermost layer, the crust, is rocky and rigid. There are two kinds of crust: continental crust and oceanic crust. Continental crust is thicker and predominantly felsic in composition, meaning it contains minerals that are richer in silica. The composition is important because it makes continental crust less dense than the oceanic crust. Oceanic crust is thinner and predominantly mafic in composition. Mafic rock contains minerals with less silica but more iron and magnesium. Mafic rock are denser than the felsic rocks of the continental crust. The crust floats on the mantle. Continental crust floats higher in the mantle than oceanic crust because of the lower density of continental crust. An important consequence of the difference in density is that if tectonic plates happen to bring ocean crust and continental crust into collision, the plate with oceanic crust will be forced down into the mantle beneath the plate with continental crust. Earth's lithosphere and asthenosphere. In between the mantle and the crust lies lithosphere and asthenosphere. Lithosphere, the rigid outer shell of the Earth composed of both the crust and the uppermost solid part of the mantle. It is a strong, brittle layer. Asthenosphere lies beneath the lithosphere. While mostly solid, it behaves more like a viscous fluid due to the high temperatures and pressure. It allows the lithosphere plates to move and interact. Earth's mantle. The mantle is the thickest layer of Earth situated beneath the crust and above the core. It is a dynamic complex region that plays a crucial role in shaping the Earth's surface. Here is a breakdown of its key characteristics. Primarily, it is composed of silicate rocks rich in iron and magnesium. Its composition is ultramafic, that is, having more iron and magnesium than silica. These rocks are solid, but under the immense pressure and high temperature, they behave like a very viscous fluid. The movement of molten rock within the mantle pushes and pulls on the Earth's crust, causing the tectonic plates to move. Temperature and pressure increases significantly with depth within the mantle. The lower mantle is extremely hot, with temperature reaching several thousand degrees Celsius. Earth's core is the very center of our planet. It is a hot, dense region that plays a crucial role in shaping our world. It is divided into two main parts, outer core and the inner core. The core, having a density of about 10 or more, it starts below the depth of about 2,900 kilometers from the surface of the Earth and extends up to a depth of 6,370 kilometers, that is, center of the Earth. It is the innermost zone of Earth. The composition of the core is believed to be a mixture of metals, iron and nickel, but the exact composition is not yet known. The propagation of seismic waves as observed indicate that at a depth of 2,900 kilometers, velocities of P waves suddenly decreases and velocities of S waves go to zero. It is believed that the outer core must be liquid since S waves velocities are zero, which cannot travel through the liquid medium. Again, at the depth of about 4,800 kilometers, the velocity of P wave suddenly increases, indicating a solid inner core. The core's extreme temperature are primarily due to the decay of radioactive elements and the residual heat from the planet's formation. The temperatures ranging from approximately 4,400 degrees Celsius in the outer regions to 6,100 degrees Celsius near the inner core. The movement of molten metal within the outer core generates Earth's magnetic field through a process known as geodynamo. This magnetic field shields us from harmful solar radiation and cosmic rays. Propagation of P and S waves. By studying how P and S waves travel through the Earth and how they interact with its different layers, scientists have been able to piece together a detailed understanding of our planet's interior structure, including its composition, density, and temperature variations. Earth's discontinuities. Several discontinuities were observed during the study of the propagation of seismic waves. Discontinuities refer to the boundaries within the plate where there are significant changes in the physical properties of the material. The major discontinuities observed are Conard discontinuities. This discontinuity is between upper and lower crust. The Conard discontinuity is thought to represent change in rock composition. Then is Mohorovičić discontinuity, or simply the Moho. This is the most well-known discontinuity, marking the boundaries between the Earth's crust and the mantle. Seismic waves experience a sudden increase in velocity at this depth due to a change in rock composition and density. Then is repetitive discontinuity. This is a seismic discontinuity that marks the boundary between the upper and the lower mantle within the Earth's interior. It is located at a depth of approximately 660 kilometers below the Earth's surface. This transition is associated with a sharp increase in seismic waves velocity. Then is Gutenberg discontinuity. This marks the boundary between the mantle and the outer core. Seismic waves, particularly F waves, cannot travel through the liquid outer core, providing strong evidence of its liquid state. Lehman discontinuity. This marks the boundary between the liquid outer core and the solid inner core. This boundary detects changes in the behavior of seismic waves. Geology of Earth's exterior. Various aspects of the Earth's exterior are studied in geology, emphasizing the dynamic nature of our planet and the interconnectedness of its different components. Earth is not a uniform sphere, but rather has a layered structure, with each layer having a unique properties. Lithosphere and asthenosphere, the outermost layer of Earth consisting of Earth's crust and the uppermost part of the mantle. Surface processes. Surface processes, that is, weathering, erosion, and sedimentation, that shape the Earth's surface. We'll be discussing these processes in our next presentation in detail. Sediments and their formation. Sediments such as sand, gravel, and clay that are formed by weathering and erosion are transported by wind, water, and ice and deposited in new locations. These sediments act like a vast archive of Earth's history, allowing scientists to piece together the story of our planet's past. Geomorphology, or the study of landforms. Geomorphology is the study of Earth's surface feature and the processes that shape them. It includes the study of mountains, valley, river, coastline, and other landforms. Anthropogenic influences on geomorphic system. Human activities such as deforestation, urbanization, mining, and agriculture accelerate erosion, alter river courses, and change the landscape. Isostasy. Isostasy is a fundamental principle in earth science that helps us understand the dynamic nature of our planet. By understanding the principle of isostasy, we can better interpret the Earth's topography, predict the effects of geological processes, and gain insight into the history of our planet. It is the state of gravitational equilibrium between the Earth's crust and the mantle. It describes the concept that the Earth's crust floats on the denser mantle, much like an iceberg in water. The elevation of different parts of the Earth's surface is determined by the balance between the weight of the crust and the upward force of buoyancy from the mantle. Isostasy is an idealized model, though real-world processes are more complex. There are two theories on isostasy. Aries isostasy assumes that the crust has a uniform density and floats on a denser fluid-like mantle. The depth of the crust varies to maintain equilibrium. Higher elevation have deeper roots extending into the mantle. Pratt's isostasy assumes that the density of the crust varies while the thickness remains constant. Denser crustal material will be less elevated than lighter crustal material. Example of isostasy in action: mountain building. When mountains form and the added mass causes the crust to sink deeper into mantle, creating a deep root. Glacial rebound. After ice sheets melt, the land that was previously depressed by weight of ice rises back up. Volcanic activity. Volcanic eruption add masses to the Earth's surface, causing the crust to subside. Continental drift. The theory of continental drift, though initially controversial, revolutionized our understanding of Earth's history and dynamics. Continental drift proposes that the Earth's continents were once joined together as a single supercontinent called Pangaea and have since moved apart over millions of years. This theory was proposed by German meteorologist Alfred Wegener in 1912. Wegener's theory was initially met with skepticism and faced strong opposition from the scientific community. Evidence supporting continental drift. The coastlines of continents, particularly South America and Africa, fit together like pieces of jigsaw puzzle, suggesting they were once connected. Fossil evidence. Identical fossils of plants and animals have been found on continents now separated by vast oceans. This suggests that these land masses were once joined, allowing the organism to freely migrate. Geological features. Matching mountain ranges and rock fragments are found on continents that are currently far apart, indicating they were formed under similar conditions when they were connected. Paleoclimate data. Evidence of past glacial deposits and tropical climates in areas now located in different climatic zones supports the idea of continental movement. Significance of continental drift theory. The theory of continental drift laid the groundwork for the more comprehensive theory of plate tectonics, which explains the movement of Earth's lithosphere through the interconnection of rigid plates. Continental drift helps explain the distribution of various geological features, the elevation evolution of life, and past climate changes. The understanding of the continental drift aids in the exploration of natural resources like oil and minerals, which are often associated with specific geological formations. Plate tectonics. Plates are massive, irregular shaped slabs of solid rock that make up the Earth's outermost layer, that is, the lithosphere. They consist of both Earth's crust and the uppermost part of the mantle. These plates are constantly moving due to convection current in the mantle. The interaction between these plates at their boundaries are responsible for many of the Earth's most dramatic geological events, such as earthquake, volcanic eruptions, and the formation of mountains. Plate boundaries. The interactions between these plates at their boundaries are responsible for many of the Earth's most dramatic geological events. The convergent plate boundaries, where two plates collide. Continental collision creates massive mountain ranges such as Himalayas. Oceanic continental collision, denser oceanic plate subducts beneath the lighter continental plate, forming volcanic arcs and deep ocean trenches. Ocean-ocean collision. One oceanic plate subducts beneath the other, forming volcanic islands, arcs. Divergent boundaries, where two plates move apart. Seafloor spreading occurs, creating new oceanic crust. Mid-oceanic ridges, a prominent feature of divergent boundaries. Transform boundaries, where two plates slide past each other horizontally, often associated with earthquake. At the end of the presentation, these are self-assessment questions. Go through each question carefully. Answer these questions based on understanding of the topic. Review any concept you are unsure about. The questions are: how do scientists study the interior of the Earth? Discuss. Explain the variation in the composition and characteristics of Earth's different layers. Discuss how seismic data can be used to understand the structure of Earth's interior. Write an account on the theory of continental drift. Discuss the concept of supercontinents and their formation and breakup. What do you understand by the term isostasy? How can isostasy be used to predict the future behavior of Earth's crust? Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. Don't forget to like and subscribe the channel Dr. A Classes for more engaging lesson on core subjects of civil engineering. Thank you.